speak. So yeah, I'm talking about some ongoing joint work with Davide and Abdul. Still a bit of a work in progress, but yeah. So the thing that I want to talk about is a way for building nice metric spaces for groups to act on. And the method for doing it is going to be a variant on Sageev's construction. So what I'm going to do is, we saw it last week, we even saw it again a bit this morning, but I just rewind about Sageev's construction, but in the terminology that's going to be convenient for what I'm doing afterwards. And then say the modified version. But to get there, first I want to introduce some definitions. Right. Definition, even before the definition, so let S be a set and let P be a set of bipartitions. So just a bipartition is just a partition of S into two halves. So, and I'll mostly be calling these walls. So a wall is just a partition into two halves, this negative half space and positive half space. So an ultra filter on P is just a consistent orientation of the walls. So it's a choice of half space for each wall, and you choose these half spaces in a way that you don't get any contradictions. i.e., if you have two half spaces, H1 plus living inside H2 plus, like this, and so maybe an ultrafilter phi on P, so it's a consistent orientation. So if it's selected H1 plus, then it has to also choose H2 plus. They can't be pointing away from each other. And a filter is just, well, it's the same as this, except it's only on a subset of P. So in other words, it's an ultra filter on some subset. So example, every element in the set S determines an ultra filter just by pointing all of the walls towards it, by which I mean select the half space that contains that point. And some notation, we're going to write X hat for the set of all ultra filters on P. So this is essentially the same as what Atelier was calling X bar, except X bar had this extra structure, which I haven't given it yet. So far, X hat is just a set. It doesn't have a metric or anything at this point. So it's just a collection of all of these ultra filters. So just a couple of quick examples, even though we've seen lots of this already. If you take, if S is R2 and P is just three generic lines in R2, like this, then, well, each region gives you a possible orientation by pointing towards that. But then there's an extra one that's consistent because these cross pairwise, you can point them all outwards, and that gives you another ultra filter. So X hat is just, okay, I'm drawing edges which there aren't really an X hat, but it's the vertex set of this tree. And so the set S got made a lot smaller because it turned from a whole R2 just into 8 points. But in some sense, it also got bigger because there was this extra point that got added here that we couldn't see because there's only 7 regions here, but there are 8 vertices. And the second one, which is one that Atelier drew, is you have the Z squared grid. You take all the cubical hyperplanes, then X hat includes these lines at infinity where you point all of the vertical hyperplanes sideways, let's say, and the vertical and the horizontal ones towards 0. That gives you a point out here. That gives you these lines. And then you have some in the corners where you point all up and all right. Okay, so yeah, stuff we've seen already multiple times. But so now Sageev's construction. Sorry. Yeah. I'll try. Can you read SAG here, or is that? Yeah. Feel free to complain again if I devolve into small writing. Okay, so you start with a set and a collection of walls. And given two ultra filters, thanks. Define the distance from X to Y is, this is just the number of walls that separate. This is the same as what Atelier had. The number of walls separating X from Y. Okay, I want to write this in a slightly different way now, which at the moment will look pointlessly overcomplicated, but will make sense afterwards. Another way of saying this is counting the number of walls that separate them is the same as looking at all of the subsets of P that separate and seeing which is the biggest. So it's the same as the supremum of the set of cardinalities of C, such that C is in a subset that separates. Okay, so nothing happened there, just rewrote it. Okay, so right now, this is something you can do, but right now, this isn't a metric, this is just an extended metric that can take infinite values. If you've got infinitely many walls kicking around, infinitely many walls that separate 2 points, then you get only an extended metric. And that's not so useful. So if you start with your original set S, maybe you started with an action on S and you want to end up with an action on the dual space. If the distances are infinite, that's not good from an isometry's perspective. So you're going to want distances between points that you started with to be finite. So you just add the assumption that your walls were such that any 2 points in your original set were only separated by finitely many walls. In other words, this distance is finite. This is essentially the assumption of Sageev's construction. The distance from S1 to S2 is finite for all S1 and S2 in your set. Okay, and then once you've done this, you let X be the set of all points that are at finite distance from your original set. And the theorem is that this is a Atelier cube complex. Doesn't have to, no. Because I didn't, there was no, you could have taken arbitrarily, you could have taken infinitely many pairwise crossing walls even. And if, you take point, so each.
You're saying about higher with your answer. So you said the distance between S1 and S2.
The distance between S1 and S2. Yes. So okay. So you're right. So if your original set has pairs of points that are not separated by any walls, then they will get identified by this. And so what you could do is you could pass the subset so that there were any 2 points were separated. That's something that I'm just going to be not thinking about. And so really I'm going to identify S with its image under this map. That's a good point. Yeah. More questions? Okay, so that's Sageev's construction. So here's the modified version. So here's the example. If you take, what's a good way of writing this? Just take S to be the set of basis vectors in sequences, and P is the set of walls adjacent to the origin. So these things cross each other pairwise, but points in this set are only separate. Any 2 points are only separated by 2 walls. Hyperplanes adjacent to 0. Then the dual cube complex that you get here, it's an infinite dimensional cube, but you have to make sense of what that means. 2 points are at finite distance if they're separated by finitely many walls. So they can only, so if the origin is one of your points, which it is because it's adjacent to each of these, then you can only hit points that have finitely many ones So the X is all the finitely supported sequences. Yeah, did that answer your question? Yeah. Okay, so same deal. Let SP be a set with walls. But now there's an extra piece of information, which is that you fix a subset of 2 to the p. You fix a collection of allowable subsets of the walls. And now, given X and Y ultrafilters, define the distance from X to Y with respect to this collection C to be, well, this, but you use C instead of 2 to the p. Okay, so as before, points in your original set might be separated by infinitely many things. This distance might not be finite. So you have to add that as an assumption in order for things to make sense. So assumptions. But this time, you also have to add something for this to be a metric. Because if you just take, for example, if you just took C to be some single subset of 2 to the p, maybe a single really big subset, then triangle inequality isn't going to hold for this definition. So you need to add something to make the triangle inequality hold. And so for that, one way to do it, and maybe there are more optimized ones, but this is going to be good enough for the things I'm talking about, is to say that C is closed under taking subsets. Why does the triangle inequality hold?
Why doesn't it know?
Okay, well, okay, let's just suppose that well, okay, maybe a different problem is that this could be setting the distance between lots of different points to be 0, which it shouldn't be if I want, you know, but yeah, if you just have a single what's a good example? Let's say I'm looking at looking at Z, and I'm looking at the usual walls, half integers, and the only element that I've chosen is just the element 1/2, 1.5, 2.5, 3.5, 4.5. That's it. Now the points 0 and 2 are not separated by an element of this because they're not on opposite sides of the whole thing. And 2 and 5 are not separated by an element of this. So those two things are at distance 0. But 0 and 5 are separated, so their distance would be positive. So it's, yeah.
Okay, you're fixing a subset.
Yeah, you fix the subset and you only use that to count distances. Okay. Yeah. And so I just want to say you did it in such a way that, yeah, in that example, you can do the thing that you were picturing doing where you just restrict.
I was thinking it was only counting some walls that
right. No, you're using all the walls. You're just only using some subcollection. So I'll give an example in a minute, which will hopefully clarify things. But let me just finish this setup. So at this point, you again let X be the set of points that are at finite distance from S. And the lemma, which is what we were just discussing, is that X is a metric space. Okay, so example number 1, or example 0, is if you take C to be the entire set 2 to the p, it's clearly closed in the taking subsets because it's all subsets. And this condition, well, this metric definition is exactly the metric here. And this assumption is exactly this assumption. And so this is exactly Sageev's construction if you take the entire power set. Okay, for example number 1, I want to make a definition first. Definition, a chain in P is a sequence of walls that look like this. Here's H1, and then here's H2. So each one is separating the previous one from the last one. So it's a chain in the POC set, if you like thinking about it that way. And so example 1 is if in the setting where you can do Sageev's construction, if the dual cube complex is finite dimensional, so the cube complex you get from doing Sageev's construction, then taking C to be the set of all chains gives the Helly thickening of the cube complex, which is what Tamal was telling us about last week. Another example would be of where you use the set of all chains would be down here in this example. If you use the set of all chains, the only chains have length 1, and every two ultrafilters are separated by, well, every two distinct ultrafilters are separated by a wall. So this dual space would be the direct product of 0, 1s with the L infinity metric instead of the direct sum of the 0, 1s with the L1 metric. And then, okay, here's another example, which we'll come back to. Let S be the hyperbolic plane, and P is going to be given by geodesics in the sense of this picture. So here's a geodesic. You can see it cuts the hyperbolic plane into 2 pieces. After throwing the geodesic itself into one of those halves, that's a partition into 2. So use all of the geodesics in the hyperbolic plane and use partitions like this. So this is a very large set of walls. If you take, let's see, be the set of chains such that the distance between any 2 geodesics in your chain is at least 1. Let me write that down before I finish the sentence, such that the pairwise distances between geodesics is at least 1. Okay, now if you take 2 distinct points in the hyperbolic plane, there's only finitely many, well, there's infinitely many geodesics that go between them, but a sequence of geodesics that pairwise of distance at least 1 is finite, because they're bounded by how far apart they are. So a chain looks like this, maybe. Okay, then if you do this, then this dual space that you get is quasi-isometric to H2. Okay, so the walls are, here's a wall. Take a geodesic and it cuts the hyperbolic plane into 2 parts. The wall is just, you throw the geodesic into one of the parts, and then it's those 2. So if I tell you a sequence of walls, then I'm telling you a sequence of geodesics. So I just want the closest point. So I've got a collection of geodesics, and I want to pick closest point between the geodesics, and I just want those things, those closest points to be a distance at least 1. Oh yeah. Pairwise H2 distances. Yeah. Sorry. Yeah. So this doesn't necessarily look very interesting on its own. After with H2, you did some, and you did something, and gave you thing, and gave you something quantization H2. That point is, so you might be wondering, say, from this example, what the point of setting things up like this was. This thing was got the dual cube complex, and then you decreased it some kind of electric component to it. So you might be wondering what the point of doing things like this, but this kind of procedure, you can modify to make it work any hyperbolic space, in particular any hyperbolic group. Now, if you take a hyperbolic group with Petyt, it doesn't have any action, it doesn't have any unbounded action. So if you just hook things to give things and then take quotients, you'd only get bounded states. Whereas here, you can get back entire hyperbolic. So even though this example itself is not so exciting, it tells you that there's something that you can gain, because you can get bigger things from this procedure than you can get by just going straight on places and take quotients. So that's what that example is. So using this version of things where you take subsets of 2 to the P gives you extra flexibility, because C can be a lot smaller than the set of walls, as in that hyperbolic example, because there's uncountably many walls at any 2 points. Well, in hyperbolic plane are finite distance. So C is much smaller than 2 small. Okay, so another thing you might be wondering is why I use this ultrafilter terminology. And I want to say that the terminology can be a useful perspective to take on things. So an example is that you can say things like here's I think called the ultrafilter lemma, which is essentially just in cube complexes, it's the Helly property for half spaces, but the language is useful. This says that every filter on P extends to an ultrafilter. So an ultrafilter is just a point in X hat. So the reason I'm stating this is it's useful for making constructions, because if you want to construct some point in X hat, that means you're trying to construct an ultrafilter. This says that if you want to do that, you just have to construct a filter, and a filter is just an orientation of some of the walls. So if you want to find a point that satisfies some property, you just have to orient the walls, and then the assumption on being a filter is just in terms of pairs of half spaces. So trying to construct a point in X hat got reduced to just checking some conditions that hold between pairs of walls. And that's often an easier thing to do. So to show that this is a useful way of thinking about things, I'm going to move to an example in a sec. Oh, there's a lot. Yeah, there's a lot of points. Does that answer your question? On all of those uncountably many geodesics, yes, yeah. But the good thing is that all of them with this metric are at finite distance from the ones you can see, a bounded distance from the ones you can see.
This definition right there for a C to separate X from Y, separation.
So yeah, so a wall is a partition into two sets, and if you've got 2 points, then the wall separates those points if one of them lives in one half and the other lives in the other half. Yeah, okay. So a point in X hat is a choice of half space for each wall, and it's just saying that on this wall they chose different half spaces. Okay, so now I'm going to make a definition. So the theme is here you just got some metric space. If you make the strong assumption that C was exactly equal to 2 to the P, you actually get a strong conclusion that it's a cube complex. And so the theme is that if you want to get, you can encode properties of the metric spaces you're going to get into assumptions on C, and then you can go and try and find things that satisfy their assumptions. But in order to say things, you're going to need some extra hypotheses. So a definition, C, a set of chains in P is gluable if whenever you have two elements that look like together they form a chain, they almost lie in here. So if whenever C and C prime lie in C have C union C prime, well, are such that is a chain in the way that you're picturing. So here's C and here's C prime. So they're not kind of interleaved. You do all of one and then you do the other one. Whenever that happens, then in fact, if you throw away the maximal element of C, then their union is in C. Okay, so why did I throw one away? To answer that, I'm going to come back to this example over here. So here, an allowable chain had to have the geodesics at pairwise distance at least 1. So this thing here is an allowable chain. These guys are at pairwise distance 1. Now, if I do this, then these ones also form an allowable chain. these ones are at pairwise distance 1, these ones are at pairwise distance 1, but these two here are too close together. But if you throw one of them away, then the whole thing is now pairwise far apart. And so even though this condition looks a little bit strange, in some kind of geometric settings, it's something that will come up in a reasonable way. Like here, you genuinely need to be able to throw one of them away to regain an element of C. Sorry?
You're assuming the C are finite?
Well, in order for this picture, yeah, let's say they're fine. In reasonable settings, there's going to be a last one before this one. If there were infinitely many, then you somehow wouldn't be in this setting of distances being finite, because if this were infinitely long, then a point down here and a point over here would be infinite distance. So given that I'm restricting to things being infinite distance, these two guys should both be finite. Yeah, I'm now restricting. Yeah, so actually from now on, I think C will be a subset of, yeah, they're always going to be chains, and they might not be far apart chains like this. They probably will be, but I haven't thought about whether they will be. But yeah, they're definitely going to be chains. Probably for some things it's not strictly necessary, but it's definitely a lot easier to think about. And so yeah, so H was, so C union C prime it's a chain, but not only is it a chain, it's a chain kind of in the obvious way where you have C and then you have C prime. They're not kind of alternating or anything like this. It's generally, you finish this one before you start this one. And H is the last one that you see when you that you look at when you went across C. So it's the element of C that separates the rest of C from C prime. Okay, and we saw that example.
Does it have to be like indexed by the natural numbers or anything like that? Or
I'm just the distances here are, this is just counting. There are genuinely finitely many things separating points. So it's safe to say things are indexed by the natural numbers. Yeah.
I guess I'm wondering in the picture, like P corresponds to negative integers and P prime to the positive.
This could be infinite going off that way if you really wanted. And this could be infinite going off this way if you really wanted. The important thing is where they come together, because the point is that what you would hope is that I was just going to tell you that C union C prime was in here. That would be what would make you happy. But the problem is that in settings like this, where you've used some kind of geometric thing to define C, you need some padding. And so throwing away one element is saying that there's padding. If you add padding, then it behaves the way you want it. Yeah. So if there's a really long tail this way, that's fine. The point is when they come together. I'd better, I guess. What time is it? Well, I'm going to tell you a theorem now, and so hold on to your hat. Good. Yeah, I'm just too excited. Okay, great. So theorem. The theorem says that if C is a gluable set of chains. Thank you. Then this dual space down here, X, is one coarsely injective. So the motivation I led with was we want to be able to build actions on nice spaces. And this is saying that this is a way to build actions on coarsely injective spaces. And as Tamar told us about last week, if you have an action on a coarsely injective space, that gives you an action on an injective space, because being coarsely injective is the same as being at finite distance from your injective hull. So this is actually quite straightforward to prove using this ultrafilter lemma, this ultrafilter perspective. So I'm going to give an outline of how that goes in fewer than 8 steps. Okay, so which I meant to do before stating the theorem, but I forgot. I should write what the definition of coarsely injective is.
While you're writing,
You're asking me to multitask. Okay, I failed to multitask. What happens if you with using chains?
Yeah, that are separated.
Yeah, okay, you have to be. Are you asking if it has a cube complex? If you took chains that are so the problem for getting something that's actually you're taking chains. You're not going to get a cube complex. You're going to get something that's L infinity like an injective space. But the problem with actually getting an injective space is this padding that you did here. This padding where you threw away one thing is what's essentially responsible for the one course leaf in this statement. Yeah. So if you manage to find a discrete enough set of walls, then you end up in this thing that I said here, where in the setting of Sageev construction you get the thickening. Even if you don't have to assume that actually finitely many separates. If you just assume the longest chain is finite, then you're in an example like we had down here, where you had z to the naturals, and there you still get a Helly graph in the dual, but it's not locally finite. So it's not the thickening of a cube complex like in that example. There were lots more vertices. Those are coarsely injective. If for every set of points and radii, such that the sum of the radii is, so in the geodesic space is the same as a collection of pairwise intersecting balls, but you don't have to assume the space is geodesic if you write things this way, which is useful. There is some point of y in the intersection of all of these balls where you thicken up by delta. Okay, now I can sketch the proof of this theorem. So to prove that it's one coarsely injective, we start with a collection of points xi and radii ri, such that this condition is satisfied. And so we're trying to construct a point in this space X. This space X is a set of ultrafilters. So we're trying to construct an ultrafilter. The ultrafilter lemma says that if you want to construct an ultrafilter, you just have to construct a filter. A filter is just an orientation of some of the walls. So what I'm going to do is I'm going to pick a subset of the walls and tell you what to do with that subset. And if you pick the right subset, then feeding it back through this will give you the desired point that lies in all of the balls. So for each I, let AI be the set of all walls such that there is an element of C separating xi from H, and whose length is at least Ri plus 1. Okay, so for each I, we just got, so if here's the point, you just take all the walls that are pretty far away. That's a collection of walls. Now I just have to tell you how to orient these walls. Define, right? For each H in AI, define phi of H to be the half space containing xi. Okay. So I've told you what to do with these walls. But maybe I told you to do contradictory things, and maybe it wasn't well defined. Well, that's something that you can just check. You can check that this is where the gluability condition comes in. Using gluability, you can check that this is well defined. Phi is a well defined, and you can also use gluability to check that it's a filter. So it extends to an ultrafilter. Okay, it extends to some ultrafilter. Now, that ultrafilter has the property that there is no wall that is more than Ri plus 1 away from xi that separates it from xi. So for every I, its distance from xi is at most Ri plus 1. In particular, it lies in all of these Ri plus 1 balls. The only thing I didn't tell you was why it's in x instead of x hat, but x was all the things that were at finite distance from S. So since all of these balls were in x, the centers were in x. So since you're at finite distance from something, then you're still in x. So yeah. What time is it? I have a quarter of an hour? Less? An hour? 12 minutes. Okay. Okay. Any questions about that? Okay, so this brings me to the first use of this construction, which I'm not going to say anything, not going to spend really any time on this. Application 1 is that you can use this theorem to recover that various groups act on injective spaces, including mapping class groups and other things. This is something I'm not going to focus on. We'll hear a bit more about this type of thing. It's not the focus of this talk, I don't think, but we'll hear some about this from Abdul. This can recover geometric actions of many groups, including mapping class groups, on injective spaces. Yeah, that's all I'm going to say about application 1. Okay, so the remainder is going to be about, this was producing actions on injective spaces, but in the title there was the word hyperbolicity. So I want to talk about how to get actions on hyperbolic spaces. So in order to use this to get an action on a hyperbolic space, there's going to have to be some source of negative curvature. So far, there is no such thing. So you're going to need some assumption in order to be able to get something hyperbolic out at the end. And that's provided by the following. A chain is L separated. How do I want to phrase this? For every H1 and H2 and C, a chain C is L separated. For any two elements, any chain whose elements all meet H1 and H2 has to have length at most L. And every C and C is L separated, then we just say that the whole subcollection is L separated. So, okay, so quick examples. If you're in a tree, then hyperplanes are points, so there is no crossing. And so every chain is 0 separated. In the H2 example that I unfortunately just erased, you can check that chains are 5 separated just by doing computations in H2. And more generally, you can also just define, if you want to find some C that is L separated, you can just let C be the set of all L separated chains. It's just a set of things that you could take that would be L separated. You might want to consider subcollections for some reason, but you could just take all of them. So we wanted some source of negative curvature, and this works if C is gluable and L separated, then X is hyperbolic. Some function of L, yeah. Yeah, I think it's linear in L. And okay, so, but there is this parameter L. And if you want to get rid of that parameter L, then you can do that. If you let L increase, then as Dave asked, the hyperbolicity constant is increasing. But if you want to, the second part is just that there are natural assumptions under which you can kind of average things out and get something that covers all of those, all of the different L's. And the natural assumptions, a sequence gives rise to a single hyperbolic space, which I'm going to denote X with metric D, where D is obtained by doing some procedure to the metrics D sub CL. Okay, I better wrap up. So, okay, application 2, I'm just going to write down and then skip entirely. Yes, okay. Okay. Let me write down. Okay, so one second, then I'll come to you. So I'm not going to say more detail here, but Cat0 spaces, there is a natural set of walls, and you can let C1 be the set of all one separated chains with that set of walls. Let C2 be the set of all two separated chains with that set of walls, and so on. Each of those, by the first part, gives you a hyperbolic space. You have an infinite family of hyperbolic spaces. And C10 is seeing more information than C1 because it's harder to be 1 separated than it is to be 10 separated. So you're missing out on stuff if you restrict to any finite L. So there are situations like that where you would want to be able to include information from all of them. And what I'm saying here is that there are some natural conditions you can put on a sequence like this that apply in the setting of Cat0 spaces, such that up to combining the metrics that you get from each CL, you can make it into one hyperbolic space. You can't just take like a limit because the hyperbolicity constant is getting worse. You don't end up with a hyperbolic space, but you can average them out. So you rescale and average, and a little bit like Gromov-Hausdorff convergence type thing. If you start with H2, then you don't need to go on forever, because once you hit, like I said, all the chains are already 5 separated. So once you hit C5, that's the same as C6. Well, the set of all 5 separated chains is the same as the set of all 6 separated chains. So with H2, you don't have to go on forever. The second part is pointless. The first part is doing all the work. But in more general Cat0 spaces, that kind of thing can fail to happen, and you might need to. There exists. Well, more than there exists, we have an explicit averaging process, but there exists, and it's probably not unique. Okay, well, okay. Abdul's going to feel really let down if I don't state the final application. Okay, but I'm just going to say it briefly because I appreciate that it's nearly the end. Application 3 is to spaces with contracting geodesics. And yeah, let me just paraphrase what Abdul said there, is if S is a metric space where more geodesics are strongly contracting. Sorry, I'm not going to have a chance to define these things. So just for the people who know what they mean, then there is a hyperbolic space that is obtained from this procedure that is universal for WPD loxodromics. So anybody, so if you have a group acting on this space, then any element that acts as a loxodromic WPD on some hyperbolic space has to act as a loxodromic WPD on this hyperbolic space. Okay, and so there are various examples of spaces like this. There are Cat0 spaces. There's injective spaces by work of Abdul and Alex Sisto. There's weakly modular graphs with convex balls by Mireille Zergel and Abdul, and maybe some more. And I should also say that there's work of Stephanie Spinden, and she can produce another hyperbolic space that is a bit like this, comes from a similar kind of place. The procedure is quite different, but it winds up having some of the same properties. So if you think that's interesting, then you should go and talk to her. But yeah, sorry for taking so long.
Thanks for one more big question.
Application 1, can you recover something hyperbolicity?
Yeah. So you get a these groups, you get proper co-bounded actions on injective spaces, and a proper co-bounded action on injective space implies semi-hyperbolicity. So yeah, that's how it's obtained in the work with Tamar and Nima. Yeah, so it's the same application.